The title of this presentation is Uncertainty Evaluation of Skeleton Plutonium Activity Concentration Estimated from a Latent bone model. My earlier presentation showed that the latent bone model is a two-step process consisting of principal component analysis and a multiple linear regression, and concluded that the latent bone model approach is the preferred method for estimating plutonium concentration in the total skeleton from a selected number of bones. Sergey's presentation demonstrated that osteoporosis affects estimation of plutonium activity concentration in human skeleton and suggested to use a separate LBM model for the 14 healthy whole body cases. Sergey also discussed that the 90 bone dataset can be reduced to 18 best bones. To evaluate the LBM model for the 18 best bones and the 14 health cases, the leave one out cross-validation method is used. Leave one out cross-validation is a cross-validation algorithm that utilizes one case as a test set and the remaining 13 cases as a training set for LBM. This process repeats 14 times to evaluate the predictivity of the LBM. This figure shows the result of the LBM leave one out cross-validation for 18 best bones and 14 healthy cases. The predictivity of LBM is pretty good. When LBM predicted skeleton concentrations are compared to measured skeleton concentrations. So far, we demonstrated how the LBM is applied to estimate skeleton concentrations. The next question is, what are uncertainties of the LBM skeleton concentration estimates? This diagram explains a simulation approach developed to determine uncertainty of the LBM skeleton concentration estimate using 2 sample bones as an example. From the 14 healthy cases and 18 best bones dataset, randomly select 2 bones as a sub-dataset. Then by fitting the latent bone model for the sub-dataset of 14 cases and the 2 bones, skeleton residuals for each case were calculated and stored. Note that the residual is difference between LBM predicted and measured skeleton concentrations. This process was repeated 10,000 times to obtain the residual distributions for each case. This figure shows the LBM residuals of one simulation for each of the 14 cases. This figure shows the LBM residuals of 10,000 simulations for each of the 14 cases. The LBM residual distributions for a few cases are overlapped because of similar measured skeleton concentrations. This is the box plot of the LBM residuals for each of the 14 cases. It is clear from the box plot that the LBM residual distributions are essentially normal distributions, and the standard deviation of the residual distribution tends to be larger for cases with higher skeleton concentrations. Please note that standard deviation of the residual distribution characterizes the uncertainty of the LBM predicted skeleton concentrations. A linear regression model was fitted to estimate the uncertainty using the residual standard deviation as a dependent variable and the skeleton concentration as an independent variable. So to recap, in the last few slides, I presented a simulation approach to determine uncertainty of the LBM skeleton concentration estimate using 2 sample bones as an example. And the process was repeated for up to 6 sample bones. This figure shows the LBM skeleton concentration uncertainty estimates for 2 to 6 sample bones. So the larger the number of bones, the smaller the uncertainty of the LBM skeleton concentration estimates. This figure is a different version of the previous slide using coefficient of variation, CV, as the y-axis. And it shows that coefficient of variation is large and high variable at the low skeleton concentrations. And it becomes stable at the high skeleton concentrations. And for 4 or more bones, the CV curves have little difference, especially for high skeleton concentrations. My earlier presentation and this presentation have demonstrated that not only can we use the LBM to predict total skeleton plutonium concentrations of partial body cases with a limited number of bones, but also to estimate the uncertainty of the predicted skeleton plutonium concentrations. Now we'll apply the LBM to 6 partial body cases and also compare the LBM estimates with the simple average method discussed in George's presentation previously. The table shows 6 partial body cases with 2, 3, and 4 bones and the individual bone concentrations. The 6 skeleton column contains estimates by simple average and LBM. The last column is the ratio of simple average over LBM estimates. And the mean ratio for these 6 partial body cases is 1.02, indicating close agreement in terms of estimated skeleton concentration between the 2 methods. However, the standard deviations of the simple average tend to be larger than that of the LBM. In order to compare between LBM and the simple averaging in estimating skeleton concentration and its uncertainties, a similar simulation approach was used. This is a slightly revised diagram by adding the simple average in the simulations. Again, using 2 sample bones as an example, 2 bones was randomly selected from the 18 bones and the 14 case dataset. latent bone model C-skeleton estimate was obtained, and in parallel, simple average of sample bone concentrations was calculated. Then, skeleton concentration residuals were stored for both methods. Note that skeleton concentration residuals for the simple average are not predicted minus measured as in the LBM, but it's the difference between sample bone average and measured. This figure shows the simulation results to compare estimated skeleton concentration and its uncertainties between LBM and the simple average. The blue bar represents simple average method, and the green bar represents LBM method. The x-axis is the number of sample bones from 2 to 5, and the y-axis is RMSE, root mean square error of residuals of 14 cases. See the RMSE formula at the lower left corner of the figure. Let me emphasize that RMSE is the average of residuals over 14 cases, and it is used to compare the two methods. For both methods, the larger the number of bones, the smaller RMSE, or the better the skeleton estimate. And similarly, the larger the number of bones, the smaller the standard deviation of RMSE, or the smaller uncertainties of skeleton concentration estimates. However, compared to the simple average method, it is clear that LBM is substantially better in skeleton concentration estimate. In fact, LBM improves skeleton concentration estimate by 58% and reduces its uncertainty by 67% on average over 2 to 5 bones. In summary, a simulation method is developed to determine uncertainty of LBM skeleton concentration estimate, and compared to the simple average method, LBM improves the accuracy of skeleton concentration estimate by 58% and reduces its uncertainty by 67%. Thank you.